Hey everybody, it's Mr. Mott. What I want to do is give us a little introduction to stoichiometry for AP Chem, some different ways of thinking about our chemical reaction. So if you haven't done so, this is in our packet, and it asks you to balance the equation and then write 5 true statements for this. All right. So first, in just a minute, pause the video and give yourself an opportunity to balance the equation. And once you think you got it, or you're completely stuck, go ahead and hit play. All right, so now you've had an opportunity to balance the equation. This is how I would go about it. Typically, they say, as sort of a guide or a tip, they say balance the O's and H's last. So I see that I've got 2 carbons on the left and only 1 on the right on the product side, so I'm going to add a 2 in front. I always add the numbers in front, the coefficients. We can never change the formula that's going on here. All right. So carbons are now balanced. Then I've got the O's and I got my H's. Now on the product side, I've got 2 H's, and then on the reactant side, I have 6. So because these are both even numbers, I would probably proceed with balancing the H's. If we look at the O's, I've got 2 on the left-hand side, on the reactant side from the oxygens, but I've got 2 times 2, which is 4, plus the 1, which is 5. So I have an even number of 2 oxygens on the reactant, an odd number on the product side. So that's going to make it harder. So that's why I'm going to balance the H's, and I'm going to do so by adding a 3 in front, because the 3 is going to distribute. I have 3 times 2, which is 6, which matches my 6 hydrogens on the reactant side, on the left-hand side. All right. So everything is balanced except for the O's. So then on the reactant side, again, I still have 2. On the product side, I have 2 times 2, which is 4, plus 3, which is 7. So to balance that out, what we can do is temporarily put a decimal or a fraction here and put 3.5. And we typically don't like to have a decimal or a fraction here. So your fix is to multiply everything by 2. So just like in math class, if you do something to the left-hand side and the right-hand side of an equation, you haven't changed it, that's kind of what we're doing. So what this is going to turn into is that this 2 is going to distribute to everything. So my new equation is going to be 2C2H6. 2 times 3.5 gives me 7O2. 2 times 2 is 4, so 4CO2. And 2 times 3 gives me 6H2O. And that's our balanced equation. All right. Now once we have this, we're going to ask you to write 5 true statements about this equation. And so what you want to try to do is draw upon your previous knowledge from baby chem and see what you can come up with as far as how you would sort of think about this equation and what the equation tells us. All right. So pause the video, take about 5 minutes. If you want to do a little Googling, you can do that. But see what you can come up with 5 true statements that are related to this balanced equation. When you're done or you're stuck, go ahead and play the video, but give yourself a few minutes to think about it. All right, so you're back now, and we're going to take a look at our balanced equation and see what it tells us. So there's a few different ways that we can think about the balanced equation. We can think about it on the small scale or the big scale. On the small scale, what I could say is that I could say, for instance, for every 2 molecules of C2H6, I need 7 molecules of O2 to completely react. So one thing that we're doing here is that we are comparing the reactants to each other. So for every 2 molecules of C2H6, I need 7 molecules of O2 to completely react. I could talk about what's happening from one reactant to one product as well, and I can just sort of pick and choose which ones I want to talk about. I can say for every 7 molecules of O2, I will make 4 molecules of CO2. So I'm comparing my oxygen to my carbon dioxide here, comparing a reactant to a product. That's one way I can do that. And then I could also compare products to products here, which would be another way of approaching this here. I could say something like, for every 4 molecules of CO2 that I make, I will also make 6 molecules of H2O. And I could think about this on a small scale, comparing reactants to, or excuse me, products to products. All right, so that'd be another way that I can do that. So just writing that last part around. For every 4 molecules of CO2 made, I will also make 6 molecules of H2O. So what we're doing here is that we can think about our balanced equation on a small scale, and that would definitely be something that we could do. Now, typically, we don't think about a balanced equation on a small scale because I can't measure out or count out a certain number of molecules of a substance. Typically, we think about this in moles, all right? So what I'm going to do is I'm going to rewrite my equation, or since I'm on the iPad, I can grab this and copy it. And then move down here, I'm just going to paste this here. And then we're going to talk about this more on a big scale. All right? And let's do it in gray here. So a lot of times, instead of thinking about these on the small scale, we think about it on the big scale. And from baby chem, what you may remember is that these numbers in front, these coefficients, they represent moles. Now, so everything in gray here represents moles. All right. Now, before I forget, sometimes when we abbreviate moles, especially in your textbook, it would just be MOL. To me, this isn't much of an abbreviation. I typically write it as the lowercase n. All right. So typically, I'll either write the word moles out, or I might just write the lowercase n. I typically do not use this, although you will see this in many, many textbooks and online. All right. So let's look at everything in context of moles here, and we can write some new statements. For every 2 moles of C2H6, I need 7 moles of O2 to completely react. So this is one way that when we're looking at an equation that we can compare them on a big scale, recognizing that these coefficients, these numbers that are in front, these represent moles. Okay, and so I can basically just replace any time that I talked about molecules in a previous sentence, I can basically replace them with moles. All right. So if I wanted to maybe do something a little bit different, or I guess let's do something very similar. In the previous part, the second one we talked about oxygen compared to CO2. So let's go ahead and do that again. And so I could say something like, for every 7 moles of O2, I will make 4 moles of CO2. So what this does is that it compares our reactant oxygen to a product here. And basically what you can do is you can compare reactants to reactants, which is very common. You can compare reactants to a product, okay, in any sort of combination you have. And then also products to products. And depending on what you're asked to do, we can also look at, depending on what you're asked to do, depending on sort of how you view things, and depending on the problem, you might be wanting to compare products to products or reactants to reactants. It's really how you decide how to solve certain problems and how you think about them. And we'll touch more on that later. All right, thanks for watching.